We consider any square matrix with n rows and n columns A, whose entries are A11, A12 up to A1n, second row A21, A22 up to A2n, and last row AN1, AN2, and lastly ANN. We call determinant of A number that we obtain combining in a suitable way, maybe a little bit elaborate, as we will see, its entries. That number gives an outstanding overview on some properties of the matrix, and it can be interpreted and used both in an algebraic sense and under a geometric point of view. If the entries of the matrix are real numbers, then the determinant also is a real number. The determinant can be introduced in several different ways. For instance, we might introduce it in an axiomatic way as the only function whose domain is the set of square matrices with assigned number of rows and columns, and the codomain is the real straight line associating to any matrix that number with 4 properties. The first property is that the determinant of the identity matrix is 1. The second property can be obtained changing 2 rows of A in order to produce a new matrix B, where the first row coincides with the second row of A and the second row coincides with the first row of A. Actually, B has 2 rows that has been twisted in position. Well, changing 2 rows, the determinant will change sign. And this is the property number 2 of the axiomatic approach. The determinant of B will be equal to minus the determinant of A. The third property of the axiomatic approach concerns a matrix where one row, for instance the first, is obtained multiplying the elements of A by the same coefficient C. Let's introduce the matrix capital C, where the first row is equal to the entries of A multiplied by C, and the other rows are identical to the corresponding entries in the matrix A. Well, then the determinant of the matrix C is equal to the coefficient multiplying the determinant of A. The fourth property of the axiomatic approach concerns a new matrix D that has been obtained changing the first row of A with a row that has been obtained by adding the first and the second, for instance, row. Then D has in the first row the elements A11 plus A21, A12 plus A22, up to A1n plus A2n, while the other rows of D are identical to the corresponding rows of A. If one matrix has one row that is sum of 2 others, the determinant won't change. Then the property is that the determinant of A is equal to the determinant of D. Well, this is nothing but the beginning of the axiomatic approach that's super interesting but very abstract. I prefer to proceed in a more constructive or concrete way and describe you directly a procedure for the calculation of the determinant that we will take as if it was the definition. It is based on the so-called Leibniz rule or Leibniz formula.